Hello and welcome to the NIJ Forensic Science Research and Development webinar series. Today we will hear from Kristen Livingston, a PhD candidate at the University of Central Florida, on advances in chemical sorting of commingled remains. Without further delay, I will turn things over to Kristen.
Good afternoon. My name is Kristen Livingston. I'm a chemistry PhD candidate at the University of Central Florida, working as part of the National Center for Forensic Science. Today, I will be discussing my ongoing research that focuses on how the chemistry of bone provides useful information for sorting commingled remains. This project is led by Dr. Matthew Beaudelet, my research advisor, and is carried out in collaboration with anthropologist Dr. Katie Zedlik at Western Carolina University and Dr. Jonathan Beathard at the University of South Florida. The research presented today is funded by the National Institute of Justice. However, all findings and opinions expressed are the authors and do not reflect the U.S. Department of Justice. I would also like to issue a brief content warning at this time that due to the nature of my work, images of human skeletal remains will be shown in the presentation. Commingled remains, simply put, occurs as the result of an intermixing of skeletal remains. Commingling, whether it be human-human intermixing or human-animal intermixing, poses a challenge to anthropologists who are conducting investigations. The mixing of bones can occur in both modern and archaeological contexts for a number of reasons. Mass graves that exhibit commingling can be the result of mass disasters, such as plane wrecks, which may be natural or criminal in nature. Human rights violations and wartime killings commonly lead to commingled grave sites, and also cultural or religious burial practices have been determined as a reason for commingling. Animal scavenging is another contributor to the intermixing of bones between individuals. And finally, poor excavation or recovery of remains can lead to commingling if there is a lack of proper documentation and organization during that process. Sorting commingled bones into discrete individuals, also known as reassociation, is a critical process in disaster victim identification. We know that the identity of an individual can be confirmed using DNA alone. However, DNA profiling requires DNA extraction from bone, which is a destructive process. You can imagine how time-consuming and costly it would be if DNA samples were taken from every single bone in an assemblage, just to group the bones based on the identity of the individual. And that is assuming there is even enough DNA present in each bone to analyze in the first place. Reassociation serves as a method to sort remains to their respective individuals without first needing that DNA confirmation. This is done for two main reasons. One is to maximize the number of bones recovered for each individual, and two is to minimize the number of those confirmatory DNA samples required. By first assigning the bones into preliminary groupings, much fewer confirmatory DNA samples are necessary. So now that we've talked about the importance of reassociation, how do forensic anthropologists actually go about sorting bones? I will very briefly discuss some traditional approaches, such as the use of morphology and osteometry, before taking an in-depth perspective at the more recent developments of reassociation that are based in chemistry. Physical reassociation techniques rely predominantly on the morphology of bones and are performed by trained forensic anthropologists. Such methods include visual pair matching, or evaluating if a left and a right skeletal element are from the same individual. This is accomplished primarily through the visual assessment of morphological features, but it can be complicated by the presence of bilateral asymmetry in an individual. So say you're right-handed or you are left foot dominant, there might be some asymmetry in your body. Joint articulation, or examining how bones fit together in the joints, is another tactic that is used for reassociation. For example, the articulation is shown here between the femoral head and the acetabulum. Difficulty may arise in drawing conclusions in joint articulation, however, if there is no proper fit found, which often occurs due to the lack of cartilage or tissue on the bones. Taphonomy, which includes the weathering, staining, burning, or fragmenting of bones, is also helpful for grouping remains. However, due to potential skeletal overlap in the actual grave site or the overlap of bones, multiple individuals may exhibit similar taphonomic effects, so this approach should be used sparingly. These previous methods that I just discussed are all subjective as they rely on the opinions of forensic anthropologists, and as such, the field is searching for some more objective methods to reliably reassociate bones with statistical certainty. Osteometric reassociation methods use measurements of bones and bony landmarks to determine whether bones may be correlated. These methods are continually being researched and developed, and they are increasingly using calculations that can account for intra-individual variation of bones. It is important to note that these methods are exclusionary, though, and therefore they cannot be used to conclude that a set of bones belong to the same individual. They are more used to say these bones cannot be from the same individual. Finally, the use of stable isotope analysis is rapidly growing in the field of anthropology. In stable isotope analysis, there are chemical measurements of isotopic ratios being calculated. These ratios can help determine the geographic region where an individual is from, since the different regions of the world have different isotopic distributions known as isoscapes. However, stable isotope analysis is very destructive. And in terms of resolving commingling, it would only really be applicable whenever you have commingled remains that are heterogeneous and are not from the same location. Otherwise, you risk having the bones having the same isotope ratios, and that would not be useful for reassociation. Discussion of stable isotopes is a great segue into talking about the chemistry of bone and why it may provide important information for resolving commingling and serving to help reassociation processes. So bone is comprised of two main parts, organic collagen protein and then the crystalline hydroxyapatite. If we look at the nanoscale level, we see that these mineral crystals are actually embedded within the collagen fibrils. Therefore, this means that we must take into account the presence of both collagen and hydroxyapatite when we are doing our analysis. Collagen and hydroxyapatite are the bulk components of bone, and they provide the source of major elements, including calcium, phosphorus, carbon, and oxygen. So here you can see the structure of hydroxyapatite, and there are several sites where elemental substitution can occur, and these substitutions within the bone can result in the presence of minor or trace elements in bone. So for example, the calcium in hydroxyapatite can be replaced with elements that are electronically similar to it, such as magnesium, sodium, strontium, copper, zinc. The phosphate groups could be replaced with silicon or selenium groups. The hydroxyl group is often replaced with fluorine. And then other atoms such as barium or potassium are known to adhere on the crystalline surface of our bone. So here we can see there are a lot of chemical elements that actually occur in bone and are not just those bulk components. So how can we measure the presence of these elements in our skeletal samples? Two of the most common methods used for elemental analysis are both minimally destructive surface spectroscopy techniques. The first is X-ray fluorescence spectroscopy, or XRF, and then the second that we'll talk about is laser-induced breakdown spectroscopy, or LIBS. So XRF is commonly known in the field of anthropology as an elemental analysis technique. I will give a very simplistic explanation of XRF. So we have a sample, which is going to be a bone in our case, and you shine an X-ray source onto the surface, which irradiates the material. There are electronic interactions that occur on the surface, and then those surface level atoms will produce characteristic X-rays that are emitted from the surface. And then these emissions are detected by a spectrometer and processed to produce an emission spectrum that kind of gives a chemical fingerprint of what is in your sample. So here's an example of an XRF spectrum of bone. Each of these lines or peaks that you see in the spectrum reflect the presence of a specific element within the bone. So a number of studies have looked at whether or not XRF can help with the reassociation of skeletal remains. Many of these use quantitative analysis or the actual measurement of the elemental concentrations. And they found, with varying success rates, that elemental variation can exist between individuals. So that is some promising results that kind of backs up this study that we are doing. Also, XRF is favored as an analytical technique because it is non-destructive and requires very little sample preparation. It is widely available in portable instrumentation, and then the emission spectra, like I just showed, are very straightforward and pretty simple to interpret. However, with XRF, you can detect lower mass elements such as carbon, nitrogen, fluorine, oxygen, and it also struggles to detect low levels of elements such as sodium, magnesium, and aluminum, all of which are present within bone samples. There are also no matrix matched calibration standards, which means the quantitative analysis that is performed is not really reliable. And then finally, we could argue that while the spectral output is simple, it might be too simple to detect individual variation. So now I will introduce laser-induced breakdown spectroscopy, or LIBS for short, which is my area of study and where this research project focuses on. LIBS analysis is performed on the sample surface like XRF. A highly focused laser is directed at the surface, removing micrograms of material. A high temperature plasma is formed in the process, which contains atoms representative of the sample surface. Electronic excitation processes within this plasma then produce optical emissions characteristic of the sample material, and these optical emissions are then detected by a spectrometer and processed to produce an emission spectrum, again, similar to XRF. So here's an example of a LIBS emission spectrum. You can see that it has a lot more emission lines than that of the XRF spectrum we saw, and it provides us with a more extensive chemical profile of the bone. LIBS has also been studied in relation to commingled remains, but to a very limited degree. LIBS and bone studies have all had unrealistically small sample sizes, and if elemental variation was found, there's a lack of understanding about why. Our research study aims to resolve both of these problems. LIBS is a great approach for elemental analysis because it is microdestructive and has very little need for sample preparation. It is a rapid technique, and it is available in portable instrumentation, again, similar to XRF. A few of the limitations are the lack of matrix match standards, which again make quantitative analysis unreliable with LIBS, and LIBS having very limited sensitivity to low concentrations of elements, so it may not always be able to pick up on the trace elements within bone if they are at very, very low concentrations. How exactly can LIBS spectra of bones help resolve commingled remains? Let's dive into the study. To evaluate how well the chemical profiles of bone from individual skeletal remains can be grouped to the proper individual, we first needed to simulate large-scale commingling. This requires many skeletons, which is where our collaboration with Western Carolina University comes into play. Western Carolina is home to a human decomposition facility known as Forest. At Forest, willed body donors are placed either for surface decomposition or buried for future excavation. Once the bodies are fully skeletonized, the remains are processed and become part of the John A. Williams documented skeletal collection, known for short as the Jaw Collection. So far, our research has analyzed the remains of 45 individuals from the Jaw Collection. Briefly giving you some demographic information, we have 20 male and 25 female individuals whose age at death ranges from 28 to 89, with the median being 67. So the majority of our individuals are older. All of the individuals we analyzed were placed for surface decomposition, and they had a wide range of decomposition times ranging from 113 to 871 days. From each of the 45 individuals sampled in the study, we aim to take a representative sample from each individual, comprised of 35 bones, which you can see shown in green on the figure. Between 1 and 13 locations were sampled per each of these bones, which gives us approximately 194 chemical profiles per skeleton, and for a grand total, we acquired 8,388 chemical profiles. So we have a lot of data to analyze. Here's a brief video showing just how quick a LIBS spectra can be acquired using a portable LIBS instrument. The sample is held up to the laser aperture, a scan is performed. As you can see, there's not really any visual damage, and then you can see just how fast the software processes the spectra. Now that you've seen for yourself just how quick and easy the acquisition process is, I want to show you how microdestructive this process is. So it's nearly invisible to the naked eye. In this image, which is raccoon humerus, somewhere on here there is an ablation crater. We did LIBS on this humerus, but it's very, very hard to see. It actually is here on the bone. Under a microscope, we can see that the crater is about 120 microns wide, and it's also about 120 microns deep. So for reference, that is approximately the width of a human hair. LIBS is destructive. It does remove some material, but barely. Now that the sample spectra are collected, our goal is to assess how well these chemical profiles can be grouped to their respective individuals. Now, looking at the spectra visually, there is significant overlap between these spectra. So I'll zoom in so you can see it better. There are no recognizable patterns or trends that immediately clue us into which spectra belongs to which individual. And these examples here only plot 80 spectra. I have over 8,000 spectra that I want to sort. So clearly, we cannot visually classify our spectra, and we need to turn to machine learning. We first attempted to use linear discriminant analysis, or LDA, to classify these spectral profiles to their proper individual. Using the entirety of the LIBS spectra, which is around 23,000 wavelengths, or wavelength inputs, we saw a test accuracy of 63%. That's not ideal, and we believe that it's using the whole spectrum just inundates our statistical model with too many inputs, many of which are noisy and redundant and not useful for discrimination. So our next idea is to perform data reduction and get rid of all the extra variables that we don't need. This is done through principal component analysis, which recognizes where there is variation in our data and therefore helps us reduce our data to only the necessary variables for modeling. We optimize our LDA model, and now we are using principal components as inputs. We found that we can attain 87% test accuracy if we keep 200 principal components. Now, 200 is still a lot of variables, but remember that is far less than the original 23,000 variables that we were working with. So we were very pleased with our classification test accuracy of 87%, but the downside of PCA is that it's hard to extract anything meaningful from these principal components because principal components completely transform your original data. So we decided to use PCA as an informant to which of our original spectral lines were most important for discrimination. Instead of transforming our data, we wanted to see if we can pick out what areas in our original data are useful for classification. So we looked at the PCA loadings, which essentially show you how much variation is associated with each predictor. So here is our PCA loadings for each wavelength. We look at this plot and pick only the lines with the highest variation. So anything in the green box, starting at the bottom and above, we selected as our variables. We developed a PCA-based mask that retains only these variables and masks all of the others, which is why we call it a mask. In doing so, we are able to reduce our spectra from those original 23,000 variables to just 297 variables, which correspond to 29 emission lines. And these are based on the original data. They are not transformations of the data like PCA. So with these 29 emission lines selected, we were able to classify the spectral profiles of our bones to the correct individual with 87% accuracy. This matches that of the prior analysis, but it also goes above and beyond because we actually know what LIBS emission lines and therefore which elements are critical for discrimination. So those known inputs help us to derive a physical meaning. Not only do we know that there is variation between our 45 individuals, we know where that variation comes from. So if we want to understand where the elemental variation is, we can look at our spectra, and we found that there were 9 elements responsible for this variation. Almost surprisingly, we found that there is variation between the emissions of major elements, calcium, carbon, and phosphorus. Now, these are bulk components, and I expected them to be similar between individuals. However, differences in bone density or the stage of decomposition affects the physical matrix of bone. LIBS is sensitive to the physical matrix of bone, and therefore the bulk matrix is actually helping us to classify bone because LIBS can pick up on those physical matrix differences. We saw that variation also existed in potassium, magnesium, and sodium, which are minor elements. Now, these are all homeostatically regulated by the body. So, in theory, the levels of these should not be influenced by variation in individuals' diet. However, because we see discrepancy, this clues us into the presence of metabolic dysfunction or health deficiencies that may cause variation in these elements. And then finally, we see that trace elements of barium, strontium, and aluminum also exhibit variation between individuals. So barium and strontium are widely known to be dietary indicators since there is no known regulation pathway in the body. Aluminum, though, is not a bioessential element, so its presence and variation in bone is likely attributed to environmental exposure, most likely through diagenic effects or interactions with the soil. I want to show a more visual representation of our LDA classification results. So in this figure, each of the dots are numbered and they are representative of an individual in our study. So there's 45 total. The color of each dot represents the classification accuracy. So based on the scale on the side, red is poor classification, and then blue and purple, you have your much better, good classification accuracy. There's arrows going between the dots. So these arrows occur where there are misclassifications in our model. So where the profile that is belonging to one individual gets misclassified as a different individual. So the arrow shows you who it is misclassified as, and then the width of each arrow shows you like the relative weight or how many times misclassifications occurred between those individuals. So there are 12 individuals shown as purple dots on the screen that had 100% classification accuracy. There are 17 other individuals that have 90% accuracy or greater. So again, we are very pleased with these results. However, because misclassifications do exist, we wanted to check and see if there's known correlation between the misclassifications. We looked at how biological sex, age, and duration of decomposition affected our predictions and found that there was no real proof that the bones of individuals who share these factors will associate. So for biological sex, only 43% of the misclassifications that we saw occurred between individuals who had the same biological sex. Same with age at death. Only 40% who were within like a 5-year age range were misclassified. And then for duration of decomposition, only 34% of individuals who had like a similar decomposition time or duration were misclassified. So these factors were not clearly responsible for why misclassifications occurred. However, we did find that the actual date of acquisition, the day I analyzed the individuals, had a very clear impact on the misclassifications. 96% of the misclassifications occurred were with individuals that I analyzed on the same day. From this last finding, we can conclude that it is instrumental conditions responsible for these misclassifications, and we are actively working to modify our sampling protocol and investigate this issue further. However, I would like to reiterate, we still only saw 13% of the spectral profiles misclassified. So this was only an issue for 13% of the data. Through this research, we have had great successes. I have created a very large data set of LIBS spectral profiles. PCA-assisted LDA was able to classify spectral profiles with 87% test accuracy. We have shown that LIBS is sensitive to physicochemical variation between individuals, even identifying where elementally that variation can be seen. We do need to do more work evaluating these instrumentation effects that I just discussed, but overall, we can conclude that the chemical profiling of bone complements the physical profiling of bone. A couple of limitations I would like to briefly point out in our study are that one, our sample set is very idealized and controlled. All of the individuals were decomposed on the surface at forest, so our findings may not apply to bones that are recovered in other settings, such as those who have been buried or found underwater. Also, there is diversity among our sample population. We had a lot of different age ranges. We have difference in residency of our individuals. However, the variation that we see in our study might not show up as prominently for a more homogeneous population. Additionally, we use supervised learning as our statistical modeling. So LDA is a supervised learning technique, which means it trains on known samples that the user tells the algorithm. Now, in the real world, in commingling situations, there are no known remains. So our study remains as just the proof of concept that chemical variation exists between remains or between individuals until more sophisticated machine learning algorithms can be evaluated without training data. Lastly, I would like to talk about the future of this project. The NIJ grant has funded our study for a total of 60 individuals, which means that there are 15 more individuals to analyze. My hypothesis is that the physicochemical variation that we saw in this study will extend to all 60 individuals. However, the accuracy may decrease slightly just due to the limitations of our linear classifier. We will also be conducting a study evaluating how the accuracy of traditional reassociation methods compare to the accuracy of the LIBS sorting protocol. While it may be easy to assume LIBS will outperform classical methods, I am more interested in seeing how we can explore a collaborative and complementary approach that harnesses the strengths of the LIBS technology and anthropologists' knowledge. Finally, we want to address the limitations of our study and move forward into future studies. So enhancing the classification algorithms is crucial if we are to apply this technique in the real world. We also want to test remains which have been found in a variety of contexts. So this past summer, I was able to collect data from medieval skeletal remains that were excavated in Transylvania. Preliminary results show that the bones from known individuals classify very well, despite a similar cultural identity and centuries spent in the ground. We are also currently negotiating a collaboration to assess how well LIBS sorting works on skeletal remains that have been submerged in aquatic environments. And then finally, we have discussed ideas on how we can further study the effects of soil conditions on the composition of bone. So to conclude, I would like to thank the National Institute of Justice for funding this amazing research. Thank you to the Forensic Technology Center of Excellence for inviting me to give this presentation. I want to acknowledge Dr. Matthew Beaudelet, who is the principal investigator of this project and a wonderful PhD advisor. my collaborators on this project, Dr. Zedlik and Dr. Bethard, the amazing undergraduates at Western Carolina who spent countless hours taking spectra with me, my research group for their endless encouragement, and then, of course, University of Central Florida and the National Center for Forensic Science for their support. So I will take any questions, and if you think of anything after the fact, I have my contact information as well as Dr. Baudelet's on the slide. So feel free to reach out and contact us.
Hey everyone, I am John Grassel, a forensic science program manager at RTI International. Kristen, thank you so much for providing that very informative presentation. We do have a lot of questions for you, which is always a sign of an informative presentation. And we will begin. And the first question is something that I'm sure many of us have is, do you have plans to study this method on buried remains in the future?
Yes, so I briefly did talk about that in my future studies work, which was getting to analyze buried skeletal remains from Transylvania. And so I have collected the data from those. So there were 17 individuals in that study were buried for, I believe they were from like the 12th or 13th century and recently excavated in the past few years. So I have collected spectral data from those buried remains and am currently working on analyzing that. Also, Western Carolina University has several remains that have been buried and are currently excavated as part of their program there. And so it could be a possibility to expand on those skeletons as well as any others that may be accessible. So yes, that is something that we are actively looking at doing.
Thank you. Our next questions deal with accuracy and measurement uncertainty. We'll start with accuracy. You mentioned 87% accuracy for the model. How does that compare to other methods that you've studied?
So I do want to reiterate that I am a chemist, and so I mainly look at chemical methods. So while I am not entirely well versed on those traditional anthropological methods, I do know that they can be quite low, like maybe 50% accuracy, which, I mean, that's kind of like 50%, yes, that it does belong to that individual, or maybe not. It's kind of a 50-50. XRF, which I mentioned, was another chemical method that has been studied. Depending on the study, some have had up to like 80-90% accuracy. I'm not giving specific values because I can't remember them right off the top of my head. And then other studies, they have not been as successful. So yeah, the big thing with this study though is that it has such a large data set, whereas a lot of those other studies have only used like a few skeletons or even a few bones. So that's something that I would like to see is like more large scale studies. Yeah.
Great. And then can you tell us a little about measurement uncertainty? So for LIBS and then for the uncertainty of your classifications.
Right. So for LIBS specifically, it's really instrument dependent. So I use a portable handheld instrument and it has its own like uncertainty with that. I am not doing any quantitative analysis on the lines themselves to find out concentration. So I don't have a uncertainty associated with a like quantitative value. When it comes to the classifications, each of the different models that I ran, I did them 10 different times with a different training and a different test set. So the variation there is going to be the error that comes from the different classification trials. Most of them were fairly consistent. I only had about 2 to 3% differences in each of the different models that I ran. So with the final 87% that we saw, most of the time, that was an average of 87%, but I saw up to, I believe it was like 90-91% and sometimes lower accuracy. So in that case, it just depended on the training and the test set, which were randomized.
Excellent. So you mentioned the handheld unit that you had, and one of our viewers wants to know, what is the general cost of that unit?
I do not know right off the top of my head. I believe it is in like the tens of thousands of dollars, but it's not cheap.
Sure. Thank you. Okay, on to our next question. What percent variability do the first and second PCs account for?
All right, so if I remember correctly, the first principal component was about 50% of the variation, and then the second was around 25%. So together about 75%. But even so, those weren't enough to differentiate or discriminate well.
And you mentioned misclassifications. So for the misclassifications, how many chemical misclassifications do you think could be resolved if you had the addition of physical characteristic information?
I love this question because our whole goal is not to replace the anthropologists and their knowledge and what they can do. And so I think it is a very good possibility that if we were to have the anthropologists alongside kind of sorting and giving information, that we wouldn't necessarily have those misclassifications because we would have their knowledge confirming whether these, or maybe not confirming, but giving their input. And so a lot of the misclassifications, which there were not that many, but a lot of them, I think when I looked at specific bones, it was a lot of long bones or like arms and legs. And those are some of the bones that anthropologists are pretty well able to reassociate. And so maybe those misclassifications wouldn't have happened if we have those anthropologists giving us their input. So I think this could be a very like strong kind of technology to work alongside those anthropologists. Yeah.
Great. And I know that you had mentioned as far as misclassification, modifying some of the sampling protocol. Would that tie into what you just discussed, Kristen?
Yes. So I briefly mentioned anthropologist informed algorithms. And part of this was because right now with our supervised learning, we do need a basis of these bones belong to this individual and then see if we can match other ones. So one idea we had was have anthropologists go ahead and do the preliminary sorting or sort some bones that they believe go together, use that information to kind of inform our model and then maybe match other bones. Or then other maybe unsupervised models that we can develop that do take into account what the anthropologists believe the grouping should be, and then kind of like give that a weighting and then take the chemical information to account and kind of just work it all together to come up with a best fit for our problem.
Thank you. And not to focus too heavy on misclassification, but one last question on it. Were there other factors besides sex, age, and decomposition evaluated for misclassification causes?
So right now, no, those were the like basic demographic or like conditional variables that I had for each individual. I know that the Western Carolina does have those more biographical profiles for each of the individuals. I haven't looked at those. And it's possible to kind of use maybe some more demographic health biographical information like that to look at misclassifications. But I think right now what we've seen that it was really the date of the acquisition that I took that was causing those misclassifications, look more into like that as a reason for misclassification.
I'm going to totally switch gears on you, Kristen. Have you used cleaning shots? And if so, how many of the shots did you use for each spot?
Yes, so the acquisition protocol that I use is 5 cleaning shots and then 20 data shots. So each spectra, like each point that I acquire, is cleaned first with 5 shots, and then it's technically 20 spectra that are averaged together into one.
Excellent. Do you think that the spectral profile of non-human skeletal elements will be different than humans? And if so, are there any plans on testing that?
So right now, we have not looked at non-human remains as part of this study. It was specifically human remains. But I do get this question almost every time that I present, like, what about animal bones? Would this be able to discriminate between human bones and faunal bones? And I don't want to say for sure that our methods could say this is animal and this is human. However, we've seen chemical differences between individuals, like human individuals, so I don't see why there wouldn't be a difference between other non-human individuals as well, right? If we're classifying different individuals, then it's likely that an animal is or a non-human is going to have a different chemical profile. So while I don't know for sure like where in the spectra that difference may come, I think that is something to look into, and to maybe incorporate human and non-human bones in a study.
Sticking with some possible future plans, are there plans to incorporate AGI, artificial general intelligence, into handheld or other units to supplement the anthropologist or forensic anthropologist that you know of?
I mean, not specifically that I know of, but I know that future studies are moving towards that. But I can't speak to that specifically.
And with the surface sampling protocol, is there any influence from external contaminant?
It's possible, that's why we do incorporate cleaning shots to see if we can get any of that like superficial exterior off. It's only a couple of microns or micrograms of that surface that we are going to be removing during the cleaning shots though. So the potential for, especially with buried remains, or it could work with surface remains too, diagenesis, where there's going to be like chemical exchange between your bone and then like the soil, for example, that is something that definitely could occur. And so if we call that a contaminant, then yes, we would like to look more into that. And again, future studies hopefully will look more into how diagenetic effects might affect the bones, maybe those skeletal samples from Transylvania that I looked at, we'll see some input because those were buried. But yes, because bones are permeable, there likely could be some chemical change due to external factors.
In the preparation of the bones for analysis, you mentioned the cleaning shots. Were the cleaning materials, did they render the remaining soft tissue, or was it performed as the bones were originally found?
So the skeletal remains that I'm working with at the decomposition facility, they are left until as much of the like tissue is removed. And then they do have some protocols that they do, but they try not to use like any chemicals or anything harsh like that. Maybe just like water and brushes to scrape off any of the remaining tissue. But yeah, it's really, there's not really tissue covering the bone at that point. It is just bone.
Excellent. Good segue to our next question. Is this method considered destructive in terms, so we have concerns from groups such as Native Americans or other groups that might be concerned?
Technically, yes, LIBS is destructive because it does take a bit of the surface material off. Now, visually, you're not going to be able to see that destruction. It is like microns, which I mentioned was like the width of a human hair. So really, you're not going to be able to see that well on the bone. So in terms of like conservation and those kinds of concerns, I think it is a good method, but yes, it is. We can't say it's non-destructive because it technically does take away a tiny bit of material.
Thank you. And do you think your ability to distinguish between individuals will increase if or when you are able to quantify the concentrations of the elements? And if so, what method is out there that you think you would like to use?
So part of me thinks that it's not actually, we see the variation not because of a major concentration difference. And a lot of it is more because LIBS is a physical spectroscopy method where a laser is actually undergoing physical interactions with the bone, and that is going to vary. The physical aspect or physical matrix of the bone affects the spectra, and that is why we're seeing that variation between individuals, because it's not just chemical, it's physical as well. But I do believe that the concentration may be another like input that we could potentially use along with just the general spectral profile, that maybe that concentration information would give us just another factor to separate. I don't think that it would be better if we were to just use concentration. Like we've seen with XRF, concentration isn't always variable between individuals, and there is a lot of measurement uncertainty too. But if we were to do like the quantitative using the concentration of elements, ideally we would have a matrix match standard, which I mentioned currently there are no bone matrix match standards available. And so that is a whole other part of my PhD research actually, is to devise and synthesize a chemical and physical matrix match standard for quantitative analysis using LIBS or XRF or any of these physical spectroscopic methods. So again, not totally getting into that, but that is something that as a chemist, we've thought about the need for a better standard.
Excellent. And do you feel that this spectral analysis of bone work for fossilized bones or other fossilized biomaterials that you know of?
I'm not sure if in terms of like differentiating for looking, so one of our future plans is to see how the spectral profile changes when bones have been submerged or underwater, and those changes, well, one of the main I don't want to say like it gets confused easily, but coral that has been underwater and eroded can potentially look like bone. So using LIBS to discriminate between bone and coral could be something that we use. But I haven't honestly thought too much about like other bone materials. It just depends. There's a lot of like need to look into like how the chemical profile of bone changes under those different processes, whether it's fossilization or being eroded or submerged and all of those things. So yeah, stuff to be studied.
If we look at missing person cases or unidentified remains cases, do you have an estimate as to when this method may be commercially available to an accuracy that could be utilized for those types of cases?
No, I don't have a time scale or anything in mind. We definitely want to be able to get the method to work with an unsupervised learning method, because that was the main drawback of this, is that it's all informed right now, but in real commingling cases, you're not going to have necessarily that these bones belong to this person, now match the rest to them, unless of course we use that forensic anthropologist informed algorithm that we're hoping to design. But again, that's the main drawback right now. Our limitation is that we need a better statistical model to kind of cluster rather than like train and then group that way. So.
Excellent. And you mentioned anthropologist informed algorithms for your future plans. Kristen, what do you mean by that?
So I feel like I've kind of answered that through other questions, but really working side by side with anthropologists as we use this LIBS technology, getting their input, having their telling what they think the grouping should be, what bones should be associated, or maybe like having them give their input, and then we use our chemical information. We can like put those together and come up with the best possible groupings, most statistically accurate. And that's a big thing in forensic in general, is that for methods to be kind of accepted, they have to be statistically proven. And so trying to come up with an algorithm where you can objectively use the chemical and the anthropological inputs.
Excellent. And how would you say that that this approach would be applicable where faunal bones are commingled with human remains?
Yeah, so again, going back to we haven't looked at faunal bones or animal bones yet, but I would hypothesize that there's going to be a chemical difference. We've seen chemical differences between just humans, and so animals, they're going to have different diets, different environments, those type of things that we hypothesize are different between human to human, so they probably are going to be different between human to animal. So incorporating faunal bones into future studies might be useful, but I believe that would still be able to pick up on those differences there.
Great. And we have had several questions related to your references or your presentation. Would you be okay with people emailing you after this presentation for reference material or other questions?
Yes, of course. I'm very happy to answer emails if you need more information or would like my references. And then also the presentation, most of the information here is currently and has been submitted for manuscript review. So hopefully coming soon, that will be published and available for people to view that way. But yes, of course, I'm very open to emails and future discussions with any of the attendees.
Great. And I'm assuming there was another question that came in about the data or the code. Would that also, do you envision, be publicly accessible?
This is a federally funded work, so I'm not sure. We'd have to check with the sponsor first, but before seeing what that accessibility for the data is going to look like. But depending on their answer, yes, I mean, I would like others to be able to use this technology too.
And do you know what platform is appropriate? I know it's a very large data set.
I use MATLAB for all of my statistical analysis, but I believe something like R could probably work too. But yeah, I specifically use MATLAB.
Thank you so much. So we have a question, which is a random hypothetical question. So if skeletal material was surface scattered and found at different periods of time due to maybe environmental or local limitations, do you think the time frame of when the bones were recovered and placed into a controlled environment may cause the samples to become more dissimilar and impact the ability to compare them?
Yeah, I definitely think that that would be a potential limitation. I mean, we've talked about the issues with the sampling protocol right now, where if you don't sample on the same day, it might not match. So especially in thinking in terms of this hypothetical, if bones were scattered in different positions or different environments, in environmental conditions definitely can impact the bone composition itself. Maybe not to a severe degree, but it's possible that the bones would not chemically match.
And I'm assuming, does the profile differ between bones within one human being?
Yes, so there is a lot of intraskeletal variation. However, the classification model that we've been using sees more similarities within an individual than it picks up on the differences between different individuals, and it minimizes that intraskeletal variation.
Thank you so much, Kristen. And if there are no further questions, we're going to go ahead and wrap up today's webinar. As Kristen mentioned, feel free to contact her for any further questions. Thank you so much for attending, and thank you for our presenter, Christian Livingston, for being here with us today.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.